As I was doing my career in quantum computing, this idea was becoming louder and louder. And at some point I had just to pull the trigger and go for it.
Can you try and describe how you think your brain works?
That's a weird one. I definitely have a different way to think than most people. My journey of my life is to help us perceive, predict, and control the world around us at all scales.
How do we get more people inspired and excited about this?
Well, we gotta scale S3 first of all, right?
Yes. We're here in Sherbrooke, Quebec, Canada, with CEO founder Guillaume Verdon of Extropic. Where are we?
We are next to a dilution refrigerator where we test our very first thermodynamic devices. And so we're trying to build the future of generative AI compute here. And this is our very first test. Really, we had to start here because the most macroscopic device that we could build that had the right properties needed to be super cooled, similar to a quantum computer. And so what we did was use a lot of our background from quantum computing and infrastructure that you see around me here to create a testing platform for this device. And so here we're in the lab. Later on, you're going to be in the fab, see some of these chips get fabricated. And so really exciting to be here. It's been a long time coming for me. It's been a long journey, but I'm so stoked to be here today.
Can you give a quick, for people that didn't watch the main episode and who should now, quick description of what Extropic is?
Yep.
And then what led you to founding it?
Yeah, so what we're building at Extropic, our mission essentially is to build the ultimate substrate for AI compute, right? Hit the ultimate limits of physics in terms of density, spatially, in terms of energy efficiency and speed for AI. So how do we do that? Well, we embed AI algorithms into the physics of the world as tightly as possible. And this is a prototype and test platform where we do that very embedding of generative AI algorithms into the physics of electrons dancing around, in this case in very low temperature, and later on at higher temperature. And so at Extropic, we're building a full stack, so software, hardware, reinventing the whole thing for generative AI from first principles, because today's compute wasn't made for AI. It was kind of a coincidence that we can run AI algorithms on today's GPUs. And so for us, clearly the future, there's infinite hunger for AI compute. We're reimagining the whole stack from first principles just for AI. And so we call it thermodynamic computing. It's a new paradigm of computing. It's not quantum. Very important. It's not quantum. It's not deterministic either. So it's not digital, definitely on, definitely off. It's a mixture of different states over a continuum. And essentially, we steer electron dances to give you sort of fuzzy beliefs about predictions of values of variables. What does that mean? You can essentially do a generative AI as physics of electrons directly. That's obviously super fast because electrons jiggle really quickly, and it's super energy efficient because you use as few electrons as possible, right? So this platform is as few electrons as you can go, right? Our later platforms are going to use more electrons, are going to be hotter, but this is really hitting the limits. For us, it's sort of Tesla Roadster moment, right? It's showing the world, hey, this new paradigm is coming. It's much more performant than what you've seen before, and you should pay attention to it, right? And we're using existing supply chains and existing infrastructure as much as possible to just show the world, hey, thermodynamic computing is here and it's coming, get ready. And it's a first start. And so I'm super excited to be here today and be getting our first data. Yeah.
Amazing. What was your personal background from, I guess I'm going to say like middle school or high school? Were you always interested in compute? What took you from that all the way through like the dark labs, as you mentioned, to today?
Yeah, growing up, I was a weird kid. I was both, playing football, and also my life's mission was to figure out physics, right? Like,
where did that come from? That initial mission, was there a book?
Yeah, I think like when I was like 7 or 8, I read Stephen Hawking's works, and I wanted to understand the universe. In a sense, if you're gonna help civilization scale to the stars, which many kids want to do, and hopefully a lot of listeners are aligned with that mission. You have to understand the stack of the universe in order to figure out how to best hack it. So I spent a lot of my career in theoretical physics trying to understand the physics of the world. And then I switched to sort of engineering how to hack the physics of the world for better compute and to better understand the world around us. And so that led me from theoretical physics originally to a different type of physics-based AI. And I was actually very early on a pioneer of that subfield called quantum deep learning. So bringing sort of AI sort of thinking to quantum computing. So I wrote some of the first algorithms, was one of the first users of the first commercial quantum computer platforms with my CTO, Trevor. We ended up creating a framework that we launched with Google called TensorFlow Quantum, which was like how to do AI, how to program AI on quantum computers. So for me, that journey was how to think like the physical world, how to make computers think like the physical world sort of computes, and how to view the entire universe as a simulation in a sense. Right? So if you view everything as computation, then you know how to map it to a computer. And quantum computing was an important component. And I've paid my dues there, spent a couple of years there. And over time, we realized that there was a missing piece, right? And there was going to be a different type of physics-based computing that was going to be kind of the piece of the puzzle that was missing, right? Because you have quantum mechanical computing that's like in superpositions. It's like very weird quantum mechanical effects. You have deterministic computing, on digital computers of today, but you don't have a sort of probabilistic form of computing, right? And so what kind of physics do you need to harness there? You need to harness the physics of jiggly stuff, right? So out of equilibrium thermodynamics, right? Which is jiggly physics, right? And so that's what we're building. We're just building devices that are kind of lo-fi in the sense that they harness very noisy dynamics of electrons and make it programmable. And so we've done it. We were pioneers of doing that for quantum computing, and now we're doing it for thermodynamic computing. And so, yeah.
I have a ton of questions about like your childhood and early days that led you to this path of inspiration, but I'll leave Walter Isaacson to do that for you.
Sure.
I am curious specifically about you're young and you're thinking, I want to scale humanity through the stars.
Yep.
And you specifically eventually land on this idea of fuzzy, non-binary linear compute as the most important thing for you to dedicate your life to. Why? Why not other things?
So intelligence allows us to perceive, predict, and control our world. And my journey of my life is to help us perceive, predict, and control the world around us at all scales. So at the very, very small scales, if you want to control electrons, chemical reactions, so on, you've got to understand the quantum mechanics of the world. If you want to understand the mesoscales, right, like classical mechanics, robotics, we have deterministic computers. You can simulate, Newtonian mechanics just fine. But actually, for biology, the mesoscales, right, the jiggly stuff, right, proteins and so on, actually, I found that today's compute is pretty much, it's lacking, right? It's really hard to simulate protein folding and so on. And so just like in quantum computing, there's big benefits in understanding and simulating the world, the very small scales, by using a sort of similar type of physics to run the algorithm that represents the world, right? So we're running quantum AI on quantum computers. Essentially, running thermodynamic AI on thermodynamic computers is going to help us understand the mesoscales around us and a lot of the complexities of our world in a much more energy efficient manner. And ultimately, we're trying to unlock the maximum amount of intelligence we can get out of a single watt, right? Some people want to scale total amount of watts we produce as humans through nuclear fusion, which I believe you're talking to around here. And as a dual to that, if you maximize neural intelligence per watt, then you're maximizing the amount of intelligence in the universe by maximizing those two things. And so to me, that's kind of the ultimate mission. I've written some stuff on the internet about this that has gone somewhat viral. But to me, that's kind of been my fundamental mission, scaling the scope and scale of intelligence and civilization, right, through the universe. And so,
can you walk me through sort of your realization path from 7-8-year-old reading Stephen Hawking, realizing I want to expand intelligence to the universe to where you are today? Because I imagine it wasn't always like, I want to build a thermodynamic computer.
Yeah.
I imagine you had different realizations along the path. Can you walk me through like top level what those linearizations were?
Yeah. So, I mean, originally I was like, okay, can humans actually crack physics to a point where maybe we don't even need computers. We just have equations that are so powerful. We could predict everything. And, I got into theoretical physics, got into quantum gravity. And there it turns out that the best path forward was to convert our understanding of quantum gravity to information theory, which is, Claude Shannon, the grandfather of computing in a sense, invented information theory. And so we were looking at the intersection of physics and information theory as the path forward for theoretical physics. And to me, that was the bridge to computing. Actually, I was not going to figure out the equations, the master equations of the universe, but maybe we could program computers to understand the universe for us. And so for me, that was very humbling at a sort of crisis of faith, because originally I really wanted to figure out the theories of everything. Yeah. But then it became sort of, okay, well, maybe I can't solve the equations myself, but I can build the machine that will understand the universe. And so that's been my quest. And that's what brought me to physics-based AI, because physics-based AI is the best type of AI to understand the physical world. That's what brought me to quantum computing, pioneer quantum AI. And that's what's bringing us to thermodynamic computing. We think it's going to be helpful to understand a lot of our world more tractably and scalably.
All right. To ask one final question about your background before talking more about Extropic and your vision now, can you talk a little bit about what the experience was like working at these different quantum labs, working at Sergey Brin?
Essentially, Trevor and I and some friends at Waterloo, we were in school and we were just bright-eyed, gung-ho students. And we were hacking together these prototypes for how to bring something called differentiable programming to quantum computers, which is, the concept of behind deep learning and neural networks. And we got noticed by Google, and they offered to sort of support the project and bring us on board and launch it within the walls of Google. And so we took that opportunity. And once I was within Alphabet, we ended up scattering throughout the org. I ended up, starting a team with working for Sergey Brin at the intersection of physics and AI, working on all sorts of other quantum technologies. There, the vision was sort of how to acquire and communicate quantum information so that you can then learn representations of it, right? Completing the stack.
Cool.
And so I worked on the quantum internet, analog digital conversion, quantum communication, all that crazy stuff. But that was really cool. It was really an honor. If Sergey's listening, give me a call. I'm around. No, just kidding.
So at Google, you're basically like in the team that is on the show devs. Yeah,
reality started mimicking fiction in so many ways. Many of which I can't talk about, but it was pretty surreal when that show came out.
Cool. So one of the things I can't wrap my mind around is all the software, and even the way that I personally view software and programming is taking language abstractions and packing it down into binary ones and zeros through a bunch of different levels, right? So if you're sitting on the lowest level with this kind of computing theory you have, that there are no ones and zeros.
It's no ones and zeros.
It's analog.
Yeah.
How do you even program that? What does that look like?
You make it dance. Essentially, we have parametric programs, right? And you can optimize over spaces of parameters. That's software 2.0, or differentiable programming. That's the principle that Karpathy would say gradient descent is a better programmer than you, right? You're kind of deferring how to program the computer to optimization algorithms, right? And so that's what we're doing with these devices. They're parametric, and we optimize over the space of parameters to yield a program that does the task you want it to do, right? Just like a neural net. So it's just like a neural network, but for us, these are probabilistic programs. They're distributions, so they give you a programmable fuzz. So that programmable fuzz, you can get it to approximate your data. You can get it to approximate the output of a sensor. What was my signal input to it? There's tons of applications of probabilistic machine learning, which is basically the type of algorithm we're running on these devices as physics.
And so if you're tweaking these programmable fuzzes, are you tweaking theoretically numerical values, sine waves? Like what might that actually look like?
Yeah. I mean, it depends on the device. Some of these devices, there's all sorts of controllable parameters that affect the dynamics, but as long as there's a parameter that affects the dynamics that's controllable through a regular computer, then you can kind of tune it. You can play with it.
So this might be more similar in some ways to like tuning a wave, the way that you like music or an RF or something.
Yeah, totally.
That's pretty mind-boggling.
Yeah.
What's something when talking to people about this in this terminal space that you feel like people don't ask enough about, or that you feel like people don't like kind of just like goes over their head, or they just don't hear?
Yeah, I think a lot of people understand intuitively why it's much more energy efficient to make electrons dance. But it turns out that it's not just more energy efficient, it's actually faster. If you look at the physics of computing, actually the minimum amount of energy or the minimum amount of time it takes you to do a computation is proportional to how far you've traveled in distribution space. So how much I've had to change my fuzz, right? And because we're operating at a sub 1 bit level, we're actually taking shortcuts in distribution space. And that's why it's so fast. And so that's the key insight there. And so hopefully, as we put out more papers, people get it, but it's a very deep concept about information geometry, which, is a subject near and dear to my heart. So
very cool.
Yeah.
What's been the hardest engineering or technical challenge to date?
Yeah, I would say, figuring out the algorithmic stack was obviously a big challenge. We've made a lot of progress there. We've taken a lot of our learnings from building the algorithmic stack for quantum and physics-based AI. So that was a good set of challenges. But I would say the big one has been how to take what we're doing here and take our learnings and bring it to silicon. Right? And so there's another lab in an undisclosed location that we don't talk about yet, maybe in the follow-up documentary. But that breakthrough was a really big one, and that was the hardest one. And it's now in the rearview mirror, and we're moving fast. So, a lot of people might be familiar with how expensive and hard to scale this technology is. But for us, it's kind of a test. It's a test platform, right? For us to get the learnings and build the algorithmic stack, and then eventually port that to silicon, which obviously has much more mature supply chains, right? You would build a superconducting computer if you were an alien that didn't have earthly supply chains, right? From first principles, this is going to be the most energy efficient version of this computer, but it's not necessarily the most easily manufacturable at scale, right? And obviously, we are a company, not a science project. We would like to scale and sell our chips to everyone.
Ideally, as you said, you build these chips from aluminum. And ideally, you maybe wouldn't use all of the quantum background and experience to make these, but you're taking this experience and history you have to leverage the development and then kind of porting it all over to a silicon supply chain. What was the thought process behind those decisions? They seem like really smart ones. What was some of the thinking there and the kind of trades maybe you have to make?
Yeah.
What is that like?
Yeah. So you've probably heard our scientists talk about our first chips. They're made of aluminum. We could have gone with niobium, which has a higher superconducting temperature. So we could have run the computer maybe 100 times hotter than a typical quantum computer. We went with aluminum because that's a process that everybody knows how to do. The basic components, which we're going to see get manufactured, called the Josephson junctions, which are really important elements that give you the nonlinearity. And we started with aluminum because it was easy to manufacture, get tests, and get results quickly. And then getting to silicon, we want to use the existing supply chains and be able to scale quickly once we understand what sort of device we want to build and how we're going to map all of generative AI to physics of hardware, right? And this platform's been really useful for us, just as a sort of mental exercise, creating the software and the middleware to compile to this sort of physics, right? We can port it over to the new type of hardware. So for reference, in quantum computing, you have superconducting quantum computers, you have ion traps, some of which are in this building we can't talk about, but you have some silicon spin qubits, you have photonic quantum computers, right? You have many substrates where the software is shared. Quite a bit of the software stack is shared across these different substrates for this quantum physics-based AI. And here as well, our vision is that there's going to be many types of thermodynamic computers because it's a concept that can be applicable to many substrates. Theoretically, you can make a mechanical one if you wanted. We have some diagrams for that if you want to make one in your backyard. But this one is superconducting, and it's a place to start because if you're going to have the most macroscopic integrated circuit we can do that has these right properties where the electrons fluctuate non-trivially and we make them dance just the right way, it has to be super cooled. And as we go smaller, things are going to get hotter, which is weird sort of scaling law there.
Yeah.
So for us, we couldn't start with a breadboard prototype because that would be fake. Because then we would have to pump noise from a regular computer. And it's not natural noise. This chip uses the natural noise that would be waste heat,
right,
and uses it as an asset for computation rather than a liability, right? And that's a big breakthrough. And that's the concept we want to showcase here. And that's the sort of concept we're bringing to Silicon as well.
You are obviously a founder or the founder of EAC as well. And I think it's really interesting this week, the Zuckerberg and Dorkesh interview just released, where there's like a lot of things sort of mirrored to what the EAC community has been saying for a while, as well as other people saying different things.
Yep.
And I'm curious, I can't speak for everyone watching this, buy into the idea that we need to accelerate AI development to combat adversarial AI development. There's basically no other way to handle it.
No other way. No.
I'm curious what your personal realization journey to that was, as well as what the future of that looks like in terms of its potential development and the way we approach that problem.
Yeah, I mean, I think you hit the nail right on the head there. Essentially, it's really hard to get everyone to slow down, and it's not clear that it's the best move, even globally, even if it was tractable, right? Like, who gets to tell us to slow down? Are they more powerful than everyone? What sort of power are we giving them, right? We don't want to live in that sort of world. And, if we slow down, maybe our adversaries wouldn't, right? And so we're kind of stuck racing forwards. But I looked at sort of fundamental physics, like if you treat civilization like a big petri dish, like a sort of a biological system at civilizational scale, biological systems they just constantly shift and adapt towards growth, right? And you could think of our technologies, our techno capital machine, I'll say it, our techno capital machine has this sort of morphing system that searches over the space of technologies for the ones that are maximal utility towards our growth, right? And clearly AI is going to help us have greater mastery over our world, right? So if we want to terraform our planet, we want to, we're talking about creating lakes in Australia, right? We want to terraform Mars. If we're going to have that level of control over our world, we're going to need a ton of AI to help us, right? I think people tend to think in a too anthropocentric way. They're thinking, hey, if AI comes about, they're going to take my jobs. This is sort of zero-sum thinking. I'm thinking more in a positive sum way. Hey, we're going to do harder things. We're going to do more. There's infinite upside, nearly infinite upside in the universe out there to capture. So we're just going to try to achieve more if we have more capabilities. And so to me, in order to scale civilization to the stars, we don't have a choice but to create all sorts of AIs that are very complementary to us. We're working on physics-based AI to understand the physics of the world. And so to me, I can't think of a greater mission than that. And so we're trying to hit the, toughest problems and knock them out of the park, which, obviously getting the most intelligence per watt is a big one.
So much of society obviously is very worried about AI, but you also see this sort of like anti-technology, anti-science mind worm that feels like it's been creeping in kind of since the early 2010s, maybe 2000s. It's very potent. It's grown really fast.
Yeah.
Why do you think this is? And it's not just about AI, right? It's
about everything.
Why do you think this is? Where do you think it comes from?
Yeah, that's a great question. Where does it come from? There's various theories, right? I was kind of ground zero of a sort of viral mimetic ideology, right? It was intentional that it was going to be viral, right? So you can imagine there could be other sources of ideologies that are not necessarily in our favor, right?
It's probably easier to grow a pessimistic idea virally than a positive one. I think it is, at least.
Yeah. Especially if it's sort of confers its adherent a sort of greedy advantage, right? So if you try to decelerate others, you can rise above the pack, right? And so that's how it spreads, because people are like, you know what, y'all should decelerate over here, and we're going to accelerate and deepen our moat, right? And so there's this kind of perverse incentive, and what we've been doing is just calling that out, right? With the movement, but there's no confirmed point of origin, right? We have all sorts of theories, but what's clear is that certain players see that sort of viral mimetic movement, right, of deceleration, and are like, how can I leverage this to my advantage, right? And there's very smart players out there that make very smart moves, and some that want regulatory capture. And to us, like, slowing down innovation is like, the greatest crime against our acceleration up the Kardashev scale. And so, at least in our moral framework, that's really bad.
A question I've always wanted to ask you as like a storyteller.
Yeah.
How the hell did you grow and plan to make EAC this viral thing? Tell me about that process.
So, originally wrote the manifesto with Bayes Lord, right? I was actually founding Extropic, and I was waiting on some paperwork, right? And I was like, I have this vision for such a long time. I really want to accelerate and bring it forth, and I'm slowed down by a bunch of paperwork.
Yeah.
I was like, this is probably the last 2 weeks of vacation I'll have for the rest of my life, right?
Let's start a manifesto with those last.
Let's get into philosophy. I haven't tried my hand, and we just wrote it up, and then we tweeted it, and started a discussion, and it just kept compounding. I've always been pretty active on Twitter. I was pretty active in the quantum computing community, but then with the BEF account, I just found sort of a voice there, because I was anonymous.
Why did you realize what made you make an anonymous account? What led to that?
Well, I was in big tech, right? And I was close to some leadership, so obviously my main account was watched, and I didn't want anybody to correlate the two. So I was like, you know what? I just want to have an account where I have random thoughts, right? Yeah. And it's very freeing. People don't understand how much they restrict their thoughts until they start an account that they can say anything they want.
Totally.
Usually they test the waters by saying random stupid stuff, but then eventually they actually expose some of their inner thoughts that they never got to experiment with or even vocalize before.
Right.
Right. And for me, it's like I had all these ideas about how I view civilization that were kind of very experimental thoughts, and having this sort of low stakes anonymous environment was just the right sort of petri dish for those ideas to grow and mutate. Yeah, incubate.
Why the name Jeff Bezos?
I think back then people were like naming their accounts with the names of various tech billionaires, and Jeff Bezos was right there. I was going to do Burger Sin, but that was too close to home, so went with Jeff Bezos as the misdirection. Yeah.
Have you met or had any encounters with him about the name?
Not yet. I would love to meet Jeff. I think he's, one of the greatest entrepreneurs of all time, right? And he's contributed so much. So, I would love to chat with him, but not yet.
You talked about scaling humanity up the Kardashev scale, out of pronouncing things like that. And I think it's ironic that almost seems more possible than building a high-speed rail between Los Angeles and San Francisco.
Yeah.
And I use that as an example of like what regulatory capture has done to technological advancement. Like, it's insane that we can't do that.
Deceleration.
And so my question is, harder things like building rocket companies, because FAA allowances for that are easier than commercial air.
Yeah.
And the list goes on. Crazier things seem easier now than sort of not as hard things technologically because of this regulatory capture. How do we fix it?
It's really easy in the moment to argue and imagine like terrible scenarios and want to add a ton of process to remove that tail event downside risk. But by doing so, you also remove the tail event of upside, massive upside, right? And I think it's just like in a startup, you got to stay flexible. You don't want too much process. I think there's a sort of second law of bureaucratic complexity, just keeps increasing. And just like, in our systems, you have dissipation, and it's very crucial for the system to not blow up that there's dissipation. I think legislation and process should be sunsetted by default, right? So you have to actively renew it
Cool.
in order to sort of keep complexity low. Really, we need to refactor our code base, right? Like laws,
theoretically, a law that requires all laws to be sunsetted could be a path forward potentially.
Potentially, right? But there's all sorts of other stuff you have to modify to support that. But, you know, in a sense, like law is just code. You know, your company sits on top of this legal stack, right? And we have this dependency, and it's like having a dependency on a bloated code base will slow down your code, right? And so something has to change. I think I'm not the only one voicing my concern here. But, you know, for us to remain competitive, we need to accelerate. And so I think pushing for deregulation is definitely, you know, one way to go. And it's a good heuristic right now because adding more regulations on average does more harm than good.
What's been one of the biggest things you've learned, or some of the biggest things you've learned since founding Extropic?
I think, like, in terms of leadership, right? When you're really, well, when you at least consider yourself a very smart person, sometimes it's tempting to just tell people what to do, right? And sometimes you hire smart people and you feel inclined to tell them what to do. And I think that if you hire smart people, you should let them tell you what to do, right? Mm-hmm. And so, yes, you feel maybe less ownership of like the intellectual product at the end of the day, but that's the only way you can scale, and that's the only way we can amplify your intelligence, right? You want positive leverage over your intelligence, otherwise you're going to be a bottleneck, right? And so that's the big difference going from a small team of 5 or 10 people you manage in big tech to running a startup that needs to scale sort of infinitely, right? And so it's hiring really smart people that you trust enough to delegate with the steering of the intellectual and technical decisions of your company.
All right, this next question is a little weird, but I think it's interesting to ask people like yourself. Can you try to describe how you think your brain works?
That's a weird one. I definitely have a different way to think than most people.
Yeah.
I very much am a shape rotator to some extent, as one would say. That's a meme, but frankly, I'm bilingual, right? I grew up learning French and English, and so my intermediate representation that is common to both languages is not from any language.
Right.
It's just kind of an internal representation. And ironically for me, mathematics was the bridge because I did schooling in French and English, but mathematics, the equations were common to both. And so I tend to think in either phase space, like sort of, I tend to think sort of geometrically in a lot of the algorithms I worked on in quantum computing. I'd have a picture in my mind of some blob I try to shape and rotate and squish and move around. And then I'd go from that to equations, and then we'd go to software, and then we'd run it on a device. And it's very much how we're designing our algorithms here. I just have a picture in my mind, very much physical intuition. I think for me, it also comes from playing sports my whole life as well. Like having good physical intuition is really important. But the thing that I had to work really hard on was how to go from physical intuition to equations, right? And sometimes the equations come first to me before I even have words to explain it. And some people have grilled me on that, but that's just how my brain thinks. It's built differently. And to me, that's kind of the common latent space throughout my schooling, because again, I had to switch from French to English, right?
Yeah. What do you think most deep tech startups get wrong?
I think that, in deep tech, until like, it's all tech risk until there's, you win, right? And you got to get people to want to support you, and you got to convince the world that this is a technology that needs to exist. And some deep tech folks tend to maybe, try to build in like hyper stealth, not talk to anyone, stay hidden forever. We did that to some extent, to some minimum, until we had something we were excited about to tell the world. But I think like there's so many benefits, and we've seen this since our launch, to building a bit more in public, right? Giving the world just a bit of a preview of what you're trying to build, and explaining to the world what's your dream. Because then you get people that want to help you, people open doors for you, and you kind of hyperstition the advent of this technology. Because at the end of the day, you're trying to coerce the techno capital machine into birthing a technology you think it needs, right? And so you gotta finesse it. You gotta convince the world that this technology needs to exist, and the world is going to figure out how to give you the resources to make it happen, right? And clearly, right now, it's very street forward to convince the world that you need more AI compute much more energy efficiently. But a couple years ago,
That was not.
or 8 years ago when I came up with this idea, it was just crazy, right? Like, why would you build such a computer? AI is just like this weird set of algorithms that a bunch of folks starting this open AI, whatever that is, some nonprofit nerds, yeah, you know, like it was really small back then, but now it's kind of a no-brainer.
Yeah.
And you know, for me, it was kind of a secret idea. I thought it was too crazy for 6 years. Really, I thought it was too crazy, and I had to convince myself that it was not crazy because I failed to kill the idea.
Yeah.
Right? You try to grill yourself and you try to kill it. Like, okay, it's not going to work because X, Y, Z, but I failed to kill this idea, and it was possessing me and becoming louder and louder in the back of my mind. As I was doing my career in quantum computing, this idea was becoming louder and louder. And at some point I had just to pull the trigger and go for it. Right?
Well, I love that advice too on thinking like, how do you decide what to build? Try to kill it. Let it grow louder. I think that's good advice.
Yeah. Yeah.
So storytelling is important. Obviously, you believe that through a ton of sort of Extropic, through EAC. And I think kind of my mission with S3 is very similar and parallel, maybe slightly different. But my whole thing is like, how can we inspire more people to go and do stuff like what you're doing?
Yeah.
Do what the other people we've interviewed and made documentaries on are doing of building the future. How do we win that culture war against deceleration, against like anti-technology? How do we get more people inspired and excited about this?
Well, we gotta scale S3 first of all, right?
Yes.
But we need more of this. I think optimism, just like pessimism can be contagious, optimism is actually contagious, and so is courage to some extent.
Yeah.
Right. You know, I saw Elon growing up do all sorts of crazy stuff, and I was like, if he can do it, I can too. Totally. Right. And that's what inspired me to do this company, and hopefully we inspire people to start their own deep tech companies that are really ambitious. And if everyone starts thinking in a more ambitious fashion and inspiring each other, we can have sort of this viral mimetic movement grow. And really, we are going to live in a better future, because if everybody's working on really hard problems that are of high impact, odds are we're going to solve more big problems and we're going to live in a better world. And so that's the sort of movement we're trying to kickstart here. And I think we're doing well, but we got to keep going. So
that might have been the answer to this next question, or what you said at the very beginning. But I like to ask every founder I interview this at the end of an interview. What is your current life philosophy?
Yeah, I mean, for me, I do live the EAC values, right? Like EAC is about figuring out how you can be of service to the growth of civilization, right? What is the unique set of actions you can take within your finite lifetime to help, you know, the odds that civilization makes it to grand scope and scale, right? And to me, with my skill set, I think figuring out how to embed intelligence very tightly into the physics of the world, that's the greatest impact thing I could do with my life. And so I wake up every day fired up, right, with sort of like the fire inside and ready to run through any walls, you know, go through any obstacle that is in my path, because I so believe in this mission. Like, I care about this mission more than anything. And so I think once you find your purpose, and I would define your purpose as like the one thing, the one place you can have the most impact in the world, you got to go after it relentlessly. And so that's sort of my philosophy, and I try to not necessarily teach it, but at least make it contagious to some extent with the movement. And hopefully more people can have this mindset, because I think it's really powerful, and it's frankly a very fulfilling life. You know, I am super ecstatic to be here. I've had very little sleep past couple of days. I've been working like a maniac, but I absolutely love what I'm doing, and I love working on this every day. And so thanks so much for coming here and, you know, showcasing our very early work. And thanks for everything you do for, you know, the community and for techno-optimism at large.
Thanks, man. That means a lot. And thank you for letting me fly out here and check this out. And also, I love what you said about Elon inspiring people. Because I think for me, when I read like the first Ashley Vance biography, to really dive deep on him, that had a huge impact on me. And I never made the connection that I could potentially work in that space or have impact at anywhere near that scale. And then as I've gotten closer to it, I realized like, whoa, like, yeah, like anyone can if they're dedicated enough. But despite that, it's rare to see new civilization level impact people like begin their journey or have that level of impact. And like, you've already done that with EAC. And now you're really doing it with Extropic. So thank you for building it and being so brave and doing it because, one general inspires a whole army. That's one person. So thank you.
My pleasure. We're raising an army. Anybody who wants to join us, apply.
An optimistic techno thermodynamic army.
Yes. Correct.
Thanks, man. This is awesome.
All right. We did it. That was great.
Cool. Dude, wow. What an interview.